Hi, we Abhishek Maurya, Esther Thomas, Harmanpreet Singh of Group 14 are here to present on the paper Joint Caching and Routing in Cache Networks with Arbitrary Topology. Background. The paper mainly discusses of two important topics, caching and routing. Caching mainly stores frequently accessed content closer to the users for faster access. Routing is mainly the optimization of the communication paths. As the title suggests, joint caching and routing, it mainly involves optimizing the placement of the content and the routing of communication paths simultaneously. I would like to illustrate these terms through an example. Consider a system model which consists of user, CDN, and a backend server or zone. I users request for J files from K caches. When a request file is not found in the cache can request the corresponding file from the zone to serve the user, which is known as cache miss. On the other hand, if the requested file is already present in the cache can directly and efficiently serve the user, known as cache hit. Our objective is to minimize both cost and latency for all the user requests and files through joint optimization of content placement and routing policies. There are many papers that has been published with a similar problem statement. Prior research dealt with 2 or 3 tier topology. The main problem of joint caching and routing has been studied in a number of network scenarios like CDN, content provider networks, and so on. There were some papers that were related to limited routing options, but this simplifies the problem of routing. There are papers that were related to link capacity constraints, but they were considered in an overloaded array. In this case, all requests cannot be served and maximizing the number of served requests. There were papers that were related to routing cost minimization, but in the underloaded array. And there were papers that show studies of joint cache deployment, request routing, and content placement. The paper's contribution is mainly divided into 4 parts. Firstly, the total cost of data transfer was minimized by optimizing the placement of cache data and routing of request. Secondly, they developed an algorithm, simple content replication with single path routing, which is this integral routing, and caching fractions of coded content with multipath routing, which is the fractional routing. They also analyze the complexity of the optimization in all the cases through connections to known NP-hard problems. Thirdly, they also developed efficient algorithms to solve the hardest case of integral caching and integral routing. They also developed a polynomial type algorithm that achieves a constant approximation in maximizing the cost savings due to caching. Fourthly, they also evaluated the solutions against existing benchmarks in the edge caching. Objective of the paper is the joint caching and routing in any given topology with the aim of minimizing routing cost by considering the limited and unlimited link capacities. Unlimited link capacities means that it serves all the requests, and limited means the limited number of requests. Secondly, it should also optimize routing among all possible paths, maintaining a polynomial complexity. We can consider any topology. Here, a general topology is given, which is the AboveNet that is mentioned in the paper. So if you consider a general topology, it mainly consists of a cacher, user, as well as an origin server. So a user requests an item, and if it's present in the cache, it can be taken, or else it has to fetch from the origin server or the backend server. So here, in the AboveNet, the green represents the origin server. It permanently stores all the items, and edge nodes, which is the red in color, it receives requests from user and host caches. The internal nodes forwards request or responses. Each edge node will have cache and routing cost is determined by the delays. This objective can be explained with the help of this node. System model. The graph consists of nodes representing caches and links representing the connections between them. The objective is to minimize the cost of transferring data in the network while adhering to the constraints of cache capacities and link capacities. The cost of transferring data can be evaluated based on factors such as delay or reliability. Content routing entails selecting the sources from which to retrieve the content and the paths to take to retrieve the content. Selection and routing decisions can be made either as a whole or in parts. In integral caching, a single node may be selected as the only source for serving a request, referred to as the integral source selection. In other cases, multiple nodes may be selected as sources called fractional source selection, and the content may be served from a fraction of these nodes. For example, if a user wants an item that is cached in node A, if the entire item is present in node A, then it is called integral caching, and if it's splitted into different nodes, then it is known as fractional caching. In case of integral routing, the routing can be achieved through a single path to fulfill the request. In case of fractional routing, the routing can be achieved through many paths to fulfill the request. For example, if the entire item is present in this cache, this node, then it can only take a single path. Next, the algorithm, joint caching and routing algorithm, is explained by Abhishek.
Algorithm of joint caching and routing are divided into 3 steps, but before that, I will give you some context about it. This is a figure of a wireless network. Here you can see there's a central server, and these are basically wireless access nodes. So these wireless access node has a cache servers also, which can store cache data, and uh, with this wireless access node, users are connected. Okay, so this is a typical structure of a wireless network. So now, suppose we have some data which has to be stored in the cache servers here. Our aim is to find the optimal cache placement and routing in this wireless network. That is basically our aim. So to explain more what we are trying to achieve, I'm giving you an example. So this is basically a 5 node wireless network structure that is I've taken just for example, and these are 2 files which we are intending to store in the cache of these nodes. So if you can see, there is a cache capacity of each node. So suppose node A has a CC of a 2, which means it can store 2 files in its cache, and node E also has CC of 2, which means node E can also store 2 files in its cache. So this is the example that I will be presenting, and our aim is to optimize the placement of these 2 files in the cache of 5 nodes, such that for any request for the data routing, the delay and cost would be minimum. So before moving to the algorithm steps, there are a few terms that is important to understand. So suppose this is our example wireless 5 node structure. So if node A wants any content from node B, so node A will request that content from node B, and that request is denoted by lambda here. And the second term is if any item is placed in node, or any content is placed in node, then we denote it by X. And another term is if we consider 2 nodes, suppose node A and node B, the shortest distance between node A and node B is denoted by W. So these are the 3 terms that is important to remember for understanding the further algorithm. So the aim what we are trying to achieve, that is optimal cache placement, can be modeled as a mathematical equation here. I have put a mathematical formula with a zero intention to explain this because its proof is little difficult. So I have just put the formula to show you that uh, we can model our cost function in a mathematical term, which has the component as the node request, all the node request, and cost factor of each node request. So these are the terms that we saw in previous slide. So these are all in the formula, and basically that our aim is formulated as a mathematical equation. Below these are the constraints which I'll be explaining in further slides with the figure. So again, there's one more formula which is basically a continuation of the previous formula. So I won't be giving the details again, but why I have put it here, because I just wanted to show you that this is a optimization equation. And what is this? What is basically optimization equation? So in the equation we have certain known parameters and certain unknown parameters. So in the optimization equation, we are basically trying to find the unknown parameters x and r such that the value of the equation becomes maximum, or basically the intuition of the formulation is maximizing the f r and r value by finding the unknowns x and r. And what is this unknown x and r? I'll be explaining in next slide. So step one of the algorithm is finding shortest path between every pair of the nodes. So in our example, we have 5 nodes here. So we would be finding shortest path between every pair of the node, and this can be found using Dijkstra's algorithm, which is an algorithm to find the shortest path between any two nodes. As example data, I can show you that for the first, consider a first row where it is basically giving a distance from node A to all other nodes. So suppose this uh, xy coordinate gives the distance between node A and B, which is 5. For example, this coordinate gives a distance between node C and node D, which is 4. So like that, we'll calculate the shortest path between every pair of the nodes. In the step 2, we are using the formula we formulated in the previous slide. That is basically an equation with the f r and r as a left hand side symbol. So we had unknowns as a x and r there, which I'll be explaining in next slide. So here I'm just trying to say that in that step 2, basically they're trying to solve the equation using pi-page rounding method. Pi-page rounding method is not explained in the paper, but if I just have to say in one line, it's basically finding the unknowns by first finding the fractional value of these x and r and then rounding it to the integer value. So using this method, they have solved the equation and found the unknown matrices x and r. So main question now is, what are matrix x and r related to this example? I'll be explaining you what is X. X is basically a matrix, and I'll be explaining with the example data. So suppose this matrix has different columns denoted by nodes and different rows denoted by the files. So these are the files which we're trying to store in all these 5 nodes. So a particular XY coordinate here, which I'm pointing here, it has a value 1, which means that node A would store file 1. Here the value is 0, it means node A will not store file 2. Similarly here, node C will store file 1 and node C will also store file 2. I'm sorry. And here the node D will store file 1 and will not store file 2. So basically X matrix denote which file should be stored in which node. And one constraint that has been considered during calculation of the optimal equation to find X is cache capacity of nodes. So each node has its cache capacity, that is a maximum limit number of files it can store, and this cache capacity has been considered while calculating X value. So now we know how cache placement is done of this two file based on X matrix among all these nodes. Now there's one more thing, that if a node wants a file, it requests to different node, and we have all the nodes which can serve this request. So the R matrix basically governs that. I'll explain you the values in this. So suppose in this matrix we have different columns again denoted by node, rows is denoted by files. So this XY coordinate, the value 0.25 means 25% of the request for file 1 would be served by node A. This value means 35% of the file 2 request by other nodes would be served by node B. So this values in this R matrix denotes that, and it basically denotes percentage of request for any file that should be served by that node. So now we are aware of the cache placement of these files on these nodes based on R matrix, and we are aware of the percentage of requests for any file that can be served by any node based on R matrix. So now what is this next step? What is step 3? So suppose, for example, if node D wants a file 2, node D doesn't have file 2, it has file 1, and if this node wants file 2, so it will ask for file 2 from other nodes. So how it will select the node? That process is called source selection process, and this is achieved by RNR algorithm, route to nearest replica algorithm, which I'll be explaining in next slide. So this RNR algorithm is not explained in the paper, but I will show you how it is used in the paper based on this example data and points. So firstly, it uses a Dijkstra's table which we created in step 1. It basically tells the shortest distance between any two pair of nodes. Second step is it takes the input as this X matrix, R matrix in this Dijkstra's table. And so for our example, if node D wants a file 2, what it does is it's basically checks the nearest node that fulfills the requirement that has the file, and that basically fulfills the R matrix requirement that it can serve particular number of a request or certain percentage of request. If that node suffice that request, it selects that node as a source. So for example, here, if it is selecting node C would be selected as a source, and the path would be node C to D for fulfilling the request of file 2 from node D. That's how RNR algorithm works. So now the algorithm is done in 3 steps. We have done the source selection for any request, and we have placed the files in the cache of the nodes properly. So now some additional information on the algorithm. So this algorithm was a case of an integral caching and integral routing. This integral caching and integral routing has been explained in previous slide by Esther. So I won't repeat it, but this case the solution of this case was considered to be NP-hard. Now, what is NP-hard? NP-hard is a class of a problem which is difficult to solve to obtain a solution that can be practically implemented. So, this problem is considered to be NP-hard problem, but this paper gives the algorithm that is basically the approximation of 1 minus 1 by E to the theoretical optimal solution. What it means that suppose 1 minus 1 by E is nearly about 63%. So it means that algorithm solution is at least 63% as good as the theoretical optimal solution. So which can be practically implemented. The algorithm complexity is denoted by this O symbol. This is O notation. We denote complexity of algorithm with this, where mod V is the number of vertices in the nodes set, mod R is the number of requests, and mod E is the number of edges. So this denotes the complexity of algorithm. Uh, why I have put this to show you that the algorithm is polynomial time running algorithm and feasible to implement in the real time. Now there is a special case of the above algorithm which is called binary caching. So what is this special case? So in this basically uh, in the example of a 5 nodes, I have put cross on the 2 nodes. So basically it means these 2 nodes cannot store cache. So a binary caching special case is basically some node are allowed to store cache and some cannot store cache. So how do we implement the algorithm here? The proof is little bit difficult. That's why I haven't put the mathematical formula, but I can explain in 3 simple terms what it is doing here. So using our cache placement step in the previous algorithm, we decide how which file will go in which node. The difference is the nodes won't store the entire file. It will only store the fractional amount of file. For example, file 1, 50% would be stored by node A, 50% would be stored by node E as an example. So fractional data would only be stored in nodes. And the second step is basically if node A requests for any file, then it will not just select the source as one node, suppose node E. It will select multiple sources. Uh, for example, it will select node D and node E for getting the file, so that the path for satisfying the request can be a multi-path, and hence the delay and the congestion in the network would be less comparatively.
Now let me walk you over the performance evaluation and the results of this paper. The proposed algorithms are evaluated against the benchmarks in the scenario of edge caching, where the data is cached at the locations which are near to user success networks. The parameters that are being measured in this paper are the routing cost, which is defined by the delays, and the congestion, which is defined by the maximum load to capacity ratio over all the links. The requests are generated in two different ways. First one are the synthetic requests, which are randomly generated requests with rate of one request per millisecond per node. Second is the trace driven. These requests are generated according to the number of views per hour of the videos that are collected over 100 hours. So let's see the results. So there are two cases. First case is the unlimited link capacity, where the links connecting the caches in the network have a very large enough capacity to accommodate all the traffic demands between the caches without any congestion. So in this case, the algorithm one proposed by the authors of this paper outperforms all the state-of-the-art solutions that are considered. So you can see the routing cost is significantly less than the other two algorithms which are taken from the other papers. First graph shows the synthetic simulations, and the second shows the trace-driven simulations. Second case is the case of binary cache capacities, where only one of the edge stores all of the cache and the rest stores no cache. So in this case, we study the congestion. For synthetic simulation, we can see that the algorithm 2 with k is equal to 1000 that is proposed by the authors of this paper performs very well with substantially reduced congestion, while the RNR has proven to be adding a lot of congestion into the network. How does this result make sense? So as per the example that are shown in the algorithm section, we take the shortest path considering the RNR, that is the route to nearest replica algorithm for source selection. Apart from that, we are optimally placing the cache based on the historical data. So the numerical data provided by the results proves that the cost for node request is quite less as compared to the other algorithms for any number of cache capacities. So here are few of the applications that we could figure out for the algorithms provided by the authors of this paper. So we can use these algorithms to store or cache the popular video content at the locations which can reduce the data transfer cost. We can use the algorithms in content delivery networks, mobile networks, Internet of Things, and cloud computing to optimize the caching and the routing costs, so that we can optimize the data transfer as well as the network efficiency. So we now study the weaknesses of this paper. So the authors doesn't consider the node or the link failures for this algorithm. So assume a node that is requesting the cache or the node which has been storing the cache crashes. This scenario is not being considered. In practice, the link capacities are often limited, but the authors are assuming the link capacities to be unlimited, which is not a realistic case because because of the traffic demands, the caches can exceed the link capacity, which can lead to congestion and increased latency. Thirdly, the algorithm lacks flexibility as the paper assumes that the cache contents are fixed and does not change frequently. So what are these are some of the suggestions that we'd like to add into this paper. So we would like to add some quality of service constraints that can help us to get a better throughput and reliability in the network. So these one of the constraint is the load balancing constraint. So we can add a term in the cost function of the JCRA algorithm by penalizing the imbalanced traffic flows among the different servers. So we don't want one of the node to be overloaded with the cache request. So there should be a load balancing technique that could distribute those requests for the cache. How this paper is relevant to our course? So this paper is closely related to the peer-to-peer systems, and these algorithms which are proposed in the paper can be very useful in optimizing and improving the overall performance of the P2P systems. So concluding, what we studied the fundamental problem of joint caching and routing in the cache network using an arbitrary topology. The objective of this paper was to minimize the routing cost under link and cache capacity constraints. The authors were able to propose and give a polynomial time algorithms that were achieved using guaranteed approximations in some of the special cases. So, according to the result, their algorithm performs better than most of the state of the art solutions that are provided by other authors. Thank you.